Hello, guys. Nice to see you.
Good afternoon, Professor.
Hi. Hello, everyone. Okay. Let's, I guess, who still wants to join will have a chance to join us during the discussion. And today we are going to continue further and start discussing kind of new topic, which is related to the previous one. But it just a bit deeper in oscillations. After oscillations, we proceed further and consider wave motion. So that's the topic we are going to deal with during this week. And so far, we considered simultaneous transfer of material like matter and energy. So if we have some motion of a body, then the mass of the body is moving in space, and as a result, also it causes changing potential or kinetic energy. So this energy also is transferred. Wave motion is a specific way, like model of motion when energy is transferred. However, matter doesn't. So in other words, just some pulses of energy, they go through the medium, and the elements of the medium, they just stay on the current position and don't move with energy transfer. So in order to realize this wave motion, we need certain conditions. So first of all, we need some disturbance, which will provide energy to the system. It could be just a single disturbance. We will talk about this. So it will provide just a single pulse, which transfers along the medium. So we also need the medium where this disturbance can be transferred through. And depends on the medium, on its properties, the transfer of waves, and also depends on the type of waves. We'll discuss this too. There will be different speed for spreading this disturbance which we provide to the medium. While the elements of the medium, doesn't matter what it is, it just be some elements of a string or a spring, can be just some volume of air. If we're talking about sound waves, they don't transfer together with energy. Okay, so probably I will change the screen. Yeah, so let us consider a simple system, which is some string attached to a wall and a bit stretched, so it has some tension. Then we provide certain disturbance at the end of this string, which goes up and down. And so it's just a single disturbance, it's not repetitive disturbance. So this disturbance will cause a formation of some single bump on this string. And it would look something like this. So, and this is kind of should be more symmetric, but yeah. So this bump, single bump on the string is called a pulse. So that happens when we have a single disturbance and we create a single pulse which moves along the string with certain speed, like certain velocity. From the location of where this disturbance was applied along the string. So if we have some periodic disturbance, if we keep going, disturbing it up and down mechanically end of this string, then we will result not in just a single pulse, but it will be already some wave which is moving along the string. And definitely wave will possess certain parameters which just single pump doesn't. That's what we will consider in future. So first of all, we need to define the types of waves. And there are two main types we can differentiate. Sometimes it happens that they are overlapping with each other, and like we get some superposition of these two types of waves. But that's what we are going to talk also about. So in this, let's consider this particular case. We see that the direction of movement of this pulse is, let's put here maybe system of coordinates just to be more clear. So this is X, this is Y. So the direction of movement of the pulse is along axis X. However, the direction of movement of the elements of this string is in the direction of Y. So when elements of the string or medium where the wave or this pulse is spreading is perpendicular to the direction of moving the wave itself, then such waves are called transverse waves. There is a different type of wave, and in order to imagine this, let's consider another system. And now we have instead of a string, we have a spring. So we have some spring under normal conditions, and then we start to apply we apply just single disturbance, but in the direction along axis X now. So it will be back and forth. In this case, we will create some regions of pressed and stretched some pressed and stretched regions of this spring. So it will look more or less something like this. So we have stretched here, then we have short pressed, and then again stretched. So this is also a wave, some pulse, which is moving along axis X. But in this case, the elements of the medium in which this pulse is moving, it also moves back and forth, but it happens parallel to the direction of the pulse movement, which is also along axis X. So in this case, the velocity vector and the displacement vectors of elements of the medium, they are parallel, and this is a different type of waves, which is called longitudinal waves. So there are, again, to summarize, two different types of waves, and that is defined by the orientation of the velocity vector of the wave and the displacement vectors of the elements of the medium where this wave is spreading. So if these two vectors are perpendicular to each other, that is transverse wave, and if it's when these vectors are parallel to each other, these are longitudinal waves. So this is kind of important definition because there are different types of waves and in different medium. For instance, sound waves is a very good example of longitudinal wave because displacements of the elements of the air happens in parallel to the direction of the spreading of sound wave. So sound wave could be represented as a combination of low and high pressure regions in air, which are spreading from the origin where this disturbance, change in pressure happens, in all directions. So it spreads in spherical, in all 4 pi degree of spreading. Okay, so there are examples, as I mentioned, different combinations of longitudinal and transverse waves. In particular, waves on the surface of water. It's a good example of combined types of waves because their elements of water are moving nearly circular passes, along circular passes when this wave is moving on the surface of water. So we have transverse movement up and down, and also longitudinal displacement of these elements of water back and forth. So another example of combined formation of two types of waves is earthquake. So we know that there are two types of waves generated because of earthquakes, and there is a difference between the velocity, the speed of spreading of different types of waves in the core of the Earth. And that's why by taking into account this difference, by recording one type of waves and second type of waves, we can determine the location of the epicenter of earthquakes. So this is more descriptive part of the waves itself, of pulses and waves in different mediums, and we define different types of these waves. So now it's important also to propose some model which will be capable of describing these waves, and we have some mathematical equations. Okay, so let us, for this purpose, consider a pulse, because it's kind of easier model first if we have just one pulse, not a wave like repetitive pulses. So it will look something like this. And let us locate the maximum, like amplitude value of this pulse at 0x. So this is our x, this is our y. And let's assume that it moves from left to right with some velocity v. So some function as y as a function of x and time, but we consider first t equal to 0. So when it's located, its maximum located at x equals 0. So y as a function of x and 0, so in given time, will be some function of x, which describes the shape of the pulse. So how do you need to understand this? So this function will give you, for any location for any element of the string, for instance, if we consider this pulse moving through a string, for every element at any location of x, it will give the coordinate of y, its displacement, and at a given time, for instance, t equals 0. So this means that it will just give you, for any x, corresponding displacement of the string y, and as a result, this function will just give you the shape of the pulse. For instance, this one is just some like some normal distribution shape. So now we need to consider that this pulse is moving, so this shape will, this y coordinates at given x, they will change over time. However, we keep in mind that the shape of the pulse doesn't change. So this function, f as a function of x, like y as a function of x, so this function is constant over time. The shape of the pulse doesn't change. Then how do we describe displacement of the elements of the string at any x and any time? So when y becomes dependent on x and t. So for this purpose, if we keep in mind that shape of the pulse doesn't change, then we can write that displacement of the elements of the medium, or in this particular example of the string, at any coordinate x at time t will be equal to the displacement of the element of the string at coordinate x minus vt and at time 0. So why? Because we don't change the shape, and this shape just moves to the right. So displacement of, if we consider, for instance, some point, let's say P here, we see that its displacement is something like 0 at t equals 0. Now, let's draw another figure, x, y, and assume that some time has passed, which is t. That means that our pulse moved to the right, because it's moving to the right. Then we can draw a coordinate for this point P. So initially y displacement was 0, and now it is, I don't know, let's mark it y prime. So if now we want to find this position of point P on the pulse after time t, and taking into account that shapes didn't change, it's not exactly correct on my image because I cannot draw them exactly the same, but we keep them in mind that the shape of the pulse didn't change. Then what we can do, we can, using this equation, instead of drawing current location of the pulse, we can just keep this shape of the pulse fixed and go left, since the pulse moving to the right. So we go left, move this point P to the left, and this shift should be equal to Vt, a product of velocity to the time. So then the displaced position of point P will be now closer to the origin of coordinate, and we can measure this distance, and this like y displacement, and this will be y prime. So this is how we can find displacement of the element of medium at any position x and at any time t, if we know the shape of the constant shape of the pulse at t equals 0. Okay. Does it make sense, guys? Do you follow this concept?
Yes. And excuse me, Professor, I wanted to clarify. So if we like draw a parallel with mass, so it is actually looks like a shift of the parabola, isn't it? Like our prime parabola is this one, is just x squared, and if we want to make some shift to the right, we add x minus 2 or x plus 2, for example, like that. So does it work in the same concept, like on the concept of shift?
Yeah, I mean, I'm not exactly sure if I understood correctly the question, but the shape of the pulse can be any function. It will be defined by the disturbance you apply. That's why doesn't matter what will be the function which describes the shape of the pulse. You always need to follow this approach, assuming that the shape doesn't change over time. And then you have some independent variable, which in this case it's x and t. So you just subtract the distance it traveled to the right, from initial position x, and that will give you the coordinate of the element at any x and t. And also, if this pulse is moving to the left, then this should be changed. So displacement of the element of the medium will be equal to x plus vt and 0t. So because pulse is moving to the left, so we need to displace the point to the right. And that's why we, instead of subtracting, we add the product of velocity and time.
Okay, thank you.
Mm-hmm. But function can be any, so we don't specify what is y as a function of x. It can be any function. Okay, so now we can proceed further and try to give more accurate definition of this of the functions itself, and also of parameters of waves. So so far we were talking about pulses. So let's us go now to the waves, some periodic pulses, which are spreading along the medium, and define some parameters of these waves. Okay, so let us assume that we attach some simple harmonic oscillator to the end of this stretched string, and as a result it creates some sinusoidal wave which is spreading from the left to the right. So if we have such system of coordinate x, y, so this is our wave. Okay, so over time it will move to the right. That means we will have something like this. Okay, so this will be t equals 0. This will be some time t. And this distance between the adjacent maximum will be v times t, like product of the speed of wave motion and time interval. Then we need also to define properties of this wave. And one of the most important is the so-called wavelength, lambda. If we measure distance between two adjacent, like neighboring maximum points, which are in the same phase, this distance is called the wavelength, lambda. It depends which kind of waves we are dealing with. It could be like meters, or can be nanometers for electromagnetic waves, but with very wide range for values. Another parameter is the period. So we can draw another figure where instead of x, we will have t time and y displacement. So over time, it will look also like this. But keep in mind, here we don't have x, but it how a given point element of the string changes its y displacement over time. And if we measure time interval between two adjacent maximum which come to this point one after another, it will be the period of this wave. And also here, this height of the peak will be the amplitude, A. Actually, here it's also true, because on the y-axis we have the same parameters, displacement of the element of the medium. So this is also amplitude. So we define what is wavelength and define what is period of the oscillation. So the units for the period is second, units for the wavelength lambda is meters. Another thing is, which is very important parameter for waves, is the frequency. And frequency is defined as the number of periods of the wave which can be fitted in the unit time. So for instance, how many periods of this wave can, how many full cycle of the oscillation, which describes the wave, can fit in 1 second, in other words. So that's why frequency is reciprocal to the period. It's 1 divided by t. And frequency units is second in minus first power. And this has its own name, which is hertz. So for instance, our electrical grid, we have alternating current in our electrical grid, and it has 50 hertz frequency. So it means that 50 periods of the oscillation can fit in 1 second. That's why, from other words, 50 times per second, the voltage changes from plus 220 volts back to plus 220 volts. So it goes from plus to minus 220 volts, then from minus to back to plus 220 volts, and then 1 period is done. So since frequency is 50, means that these changes happen 50 times per second. For instance, in Europe, in post-Soviet countries, this is the frequency, 50 hertz in electrical system. But for instance, in United States, in Japan, the frequency is 60 hertz. So they have both different frequency and voltage. So these systems are not compatible with each other. Okay, so now we defined the main parameters of the wave, and let us go for some equations which can describe the wave as a function of, to be more specific about certain example, which describes dislocation y as a function of x and t. So as I mentioned before, we attached a simple harmonic oscillator, which we described previously on during our previous discussions last week, to a string, and that results in the sinusoidal wave, which is spreading along the string. So now we can write that since we have a sinusoidal wave, we can write that y as a function of x at time t, at time 0, t equals 0, is equal to a, the amplitude, times sinus of ax. So let us find what is this coefficient a. So it's general expression, but we need to use some boundary conditions and get the expression for this constant a. So which boundary condition? For instance, at x equals 0 and t equals 0, it's here at the origin. Y is also equal 0, because this wave just starts from the origin. So what we can write is like first example, 0, 0 for x in time. This is equal to a sinus a times 0, because x is equal 0. And this is equal to 0. So this doesn't help us much, because we have 0 in the argument of sinus, and we cannot really define the constant. So what is the next time, or no, what better like this formulates this question? What is the next x coordinate when the displacement y is equal to 0? So we go from this origin, so we go to maximum here, it's amplitude, and then we go down. So here is again, we have y equals 0 at t equals 0, because we consider just snapshot of the wave. We always consider now at t equal 0. So in this case, we can write that y at, so what is this distance from here, from the origin to this point where y is equal 0 again? It's half of the wavelength, because the wavelength would be like full wavelength would be from here to here, two adjacent points with the same phases. But up to here, this distance will be lambda divided by 2. So here we have lambda divided by 2. Then t equals 0. it is equal to A sinus this coefficient unknown A times lambda divided by 2. And this is equal to 0. So this will be true when the product A lambda divided by 2 equals to pi radians, which is 180 degrees. And from here, the coefficient A is equal to 2 pi divided by lambda. So we can write that y as a function of x at 0 time equals to A times sinus 2 pi divided by lambda x. Okay, so keep this in mind. We will write it on the next slide. So what did we get? So at t equals 0, y as a function of x at t equals 0 is equal to A sinus 2 pi divided by lambda times x. So before we had this discussion how we can, if we know a constant shape of the pulse or the wave, which is given by this equation, which doesn't change in time, how we can define y as a function of x and t. For that purpose, we can write that y as a function of x and t, assuming that wave is moving from left to the right, as we mentioned earlier. It will be A times sinus 2 pi lambda x minus vt. Okay, so this is already good. Yeah, keep in mind, if this wave is moving from the right to the left, it would be x plus vt, but we stick to this. Now we stick to this case when it moves from the left to the right. Okay, now we need to do something with this velocity. Like actually it's speed here. Since it's not a parameter, we want to describe this function in terms of parameters which characterize the wavelengths. Characterize the wave, and means in terms of wavelengths and period. And that's why we want to get rid of this velocity. So by definition of wavelengths and period, we can say that the wave is traveling distance, some distance delta x, which is equal to the wavelength lambda during the time interval delta t, which is equal to the period. So that's why velocity will be delta x over delta t, and this is equal to lambda divided by t. Now we can substitute this v with lambda divided by t, and with parameters which describe our which are characteristic parameters of the wave. let us write this equation. We y as a function of x t is equal to a sinus 2 pi lambda x minus lambda divided by t times the capital T times t. And this we can rearrange a bit, so to make it in more clear form, it will be a sinus if we open this parenthesis, we will, and then factor out 2 pi, we will get x divided by L or lambda minus t divided by period t. Okay, so this is the equation which describes displacement of the elements of the string in the case of a sinusoidal wave spreading along it from the left to the right with the as a function of x and t. So at any location of this element along axis x and in any time t. So this equation already shows us the periodic nature of this phenomena which we described, this waves, sinusoidal wave, because if we consider some intervals of some points which are located at x, then x plus lambda, then x plus 2 lambda, and so on, and time intervals which correspond to these locations, which is t, then t plus capital T period, then t plus 2 periods, we will get always the same y. It will be the same displacement. So let us maybe make it more clear. Here, for instance, we have x. Let us consider the argument of the sinus of this function. X divided by lambda minus t divided by period. It will be equal to, so that's what I claimed previously. It should be equal to x plus lambda divided by lambda, then minus t plus period t divided by period t. So this is true because if we change x by lambda, we need change time by period, because in the time of equal to the period of the wave can move only certain distance, which is equal to wavelength lambda. So now if we divide all this stuff, we will get x divided by lambda plus unity minus t divided by period minus unity. So 1 and 1 we cancel out, and it will be exactly what we started with by t. So we see that with very distinct periodicity, the displacement of element of the string will have the same displacement, means that we have this sinusoidal wave, and our equation well describes these features of the sinusoidal, periodic sinusoidal wave, which is spreading from the left to the right. Okay, so I guess we are running out of time now. So next time we will consider our, go further with our discussion and introduce certain parameters which will help us to write this equation in a bit more convenient and simple form. And then we will do some mathematical manipulations with this equation to get the velocity, acceleration of different elements of the spring. And then we will derive the expression for the velocity of spreading the wave in a string based on the parameters of the string. But that will be done during our next discussion on Wednesday. Okay, guys, thank you very much for your attention. Have a good evening. Bye-bye.
Thank you, Professor. Goodbye.
Yeah, bye. Have a good evening. Take care.